So today I'm talking about the work we did at Columbia to build an R&D test stand that became the prototype for the liquid purification system in Xenon N-ton. So I'm going to talk about how we developed this and its outcomes. So the problem we're trying to address is that in all these liquid xenon time projection chambers, you're relying on the detection of ionization electrons that are released when a particle scatters. And these ionization electrons you need to drift over an increasingly long distance. And since your xenon is not perfectly pure, there are impurities that will attach the electrons along their drift and reduce the size of this signal. So you'll take what's a large signal. This is in the two-phase TPC, the amplified S2, and make it smaller and more stochastic and jagged. And furthermore, these impurities are always being released from all of the surfaces of the materials inside your detector. In these kind of TPCs, we line the walls with these reflective plastics that tend to release a lot of oxygen and other impurities. And this becomes a limiting factor in sensitivity, in particular for small signals where you have a detection threshold in the minimum number of electrons where you can see a signal. So then this is an example from the boronate 7 search, but you can think of it as also a 6 GeV win. That the expectation in Xenon 1-ton at least goes up radically with the electron lifetime from the value that we had in that particular experiment. And even at higher mass, your discrimination gets worse because of the Poisson fluctuations in this electron loss process. So this is an important factor in these experiments. So what we did prior to this experiment in all these liquid xenon TPCs is continuously take liquid xenon out of your TPC, evaporate it, clean it in a very hot getter, and then recondense it. And this is limited by the speed at which you can do this is limited by the capacities of the gas xenon pumps that power this circuit. In Xenon N-ton, we do something that has been done for a while in liquid argon TPCs, where we actually just take liquid using liquid pumps and from the bottom of the TPC, put it through a cold filter and put it back to the top of the TPC. And this is easily a factor of 10 faster in purification speed due to the more dense liquid flow. But it means that you need to use cold filters, which have a lower reactivity. So you need filters containing a material with a super high surface area per unit volume. And that tends to emanate more radon, which is the limiting background for these types of experiments. So this works for argon, but for xenon, for xenon dark matter searches, because of our crazy radio purity requirements, we need to use kind of 1% of the filter mass used by established liquid argon TPCs. And that's to capture the same amount of oxygen per unit time as those kiloton detectors in these much smaller xenon detectors because of the different temperature of xenon, leading to the higher desorption. So then we asked if this was possible before doing it. So we built this test system. This is Zclips, which is at Columbia. It's composed of 2 basic systems. There's a purity monitor to measure the electron lifetime, the amount of O2 equivalent impurities in the xenon, and a purification system containing the pump and the filter. So the purity monitor is a well-established instrument in this field of physics. I'm going to use O2 and other impurities interchangeably because O2 is the dominant impurity for electron lifetime in xenon. The purity monitor, you have a photocathode, you flash light on the photocathode that releases photoelectrons, and then you drift these over a fixed distance. And you read out the induced charge on 2 grids at the beginning and end of the drift, and the ratio of amplitudes tells you the amount of oxygen in between that attached electrons. And this one is sensitive between kind of 50 microsecond electron lifetime and 20 milliseconds, so it's over a broad range. And we want to be able to not just measure, but control the amount of oxygen. So we built this oxygen injector, which relies on permeation through a silicone membrane on the return of the gas. So we purify this purity monitor system with the traditional getter purification, in addition to the liquid circulation I'll mention. And on the return to the heat exchanger, we inject a known amount of oxygen. Then there's the CPS, this cryogenic purification system. So it's all rolled up in this little in this cylinder, this insulation vessel, but unrolled, it looks like this. We take out liquid xenon from the bottom of the purity monitor. We flow it through a liquid xenon pump, put it through this oxygen filter vessel, and then put it through, there's a particle filter to stop any particles that come out of the O2 filter. And then an instrument to measure the amount of bubbles in the returning xenon that we call this void fraction meter. And this pump is a centrifugal pump, so it's based on it operates based on an impeller which is submerged in the actual liquid xenon that creates a pressure difference that drives the flow. So that we have this pump buffer that you can see here. This is a volume that's filled with liquid xenon, and the pump is this inner volume. So you have the impeller submerged, which means that you have gas xenon in here, and you have gas xenon in this insulated pump buffer. But this shaft goes up to the motor, which you can see up here, which is outside and is warm. And that contains the same gaseous xenon that's connected to this liquid. And that's going to come up later. This pump was able to drive flows of 0.15 liters per minute of liquid. And then there's the filters that we went with. We tested two kinds of filters. So the first is this very well validated liquid argon, high surface area, copper coated particulate. So it's these spheres that have a really, really high surface area per unit mass that allows you to capture a lot of oxygen, but they also emanate a lot of radon. And then our second filter was this non-evaporable getter material, which you can heat and pump to activate and has a much lower background, though also less reactivity. So we have to model the O2 transport in this experiment. So we need a basic model. Basically, we say that the removal or the rate of change of the oxygen in your purity monitor is just the sources contributing minus the cleaning rate. So you can see how the equilibrium electron lifetime increases linear with the circulation speed of the getter, and it decreases 1 over inverse linearly with the size of the sources, which are on the order of micrograms per day, the natural sources, when you just operate the purity monitor. But when you operate the purity monitor with the full liquid circulation, it's more complicated. You're measuring the purity here, but like I said, you have this pump buffer with a different, in general, electron lifetime and purity. And then you pass that through this oxygen filter. And our parameter of interest here is defined as this epsilon. It's the fraction of impurities in the liquid xenon that are removed when the xenon is passed through this filter. So we wanted to do, the idea was that we would inject enough oxygen to swamp out any natural sources of oxygen. So we know exactly how much oxygen we're putting in. We measure what's here. We know how much we're taking out. The problem we saw is that motor, the warm gas that's attached to or in contact with the warm gas xenon, created a large introduction of impurities into the liquid on this pump buffer side. So we have to treat that somehow. We couldn't swamp it out with a higher injection rate because of the limitations of our purity monitor. If we get to a high enough oxygen concentration, we can't measure. So we have to treat this. We do this by cleaning the gas. First, we try to mitigate it by taking glass from the pump buffer and the pump motor, cleaning it and putting it back in the pump buffer. This reduces this source, but also introduces another unknown, which is when you disturb this equilibrium of concentration between the gas and liquid phases in the pump buffer, you get a net reduction in the liquid of the pump buffer. So you get, since you're cleaning this gas, you get oxygen leaving through that liquid surface. And that's another thing you have to account for. So we have these degenerate things. We have this unknown source, a source of unknown size. We have this removal rate in the pump buffer, and then we have our filtration. That's the thing we're interested in. Fortunately, you can disentangle these with a few methods. First, we vary the injection rate to several values, and that allows you to decouple this constant unknown source from the things that happen to be dependent on the concentration in the xenon. So this liquid removal and this filtration both depend on how dirty the xenon is. So if you look at several known injection rates, you can decouple the two. The next thing we do is we remove the oxygen filter and replace it with an empty vessel. That allows you to remove this unknown, and then we're able to measure this exact removal rate at the liquid surface. This is our dominating systematic. So we do this. It's in general a function of this convection mass transfer coefficient. So that's indirectly what we're measuring. And our best fit value corresponds to kind of 10 micrograms of oxygen per day being removed at this liquid surface. And it's this value of this number. And we were able to validate this roughly with a thermodynamic calculation. You can use this boundary layer approach to this problem. Assume there's a thin film that's kind of in equilibrium with the liquid, and that a thin film at the liquid surface. And then the exchange between that thin film and the rest of the gas with a much lower concentration drives the removal of oxygen. And we get something within a factor of 2 of this best fit. So we say, okay, we understand this systematic, let's fix it to the best fit, and then we can put back our filter and measure the efficiency. So that's what we did for these 2 filters. So you can see here, the concentration is the solid thing on the left axis, the concentration of oxygen in the purity monitor. So you can see we clean our xenon very well at first, and then we running this liquid circulation, and then we inject at several fixed known values. And you see with each injection, as we increase the injection rate, the oxygen concentration at equilibrium goes up. And from that, you're able to estimate the efficiency for both of these getters. So for this copper-based filter, we get almost consistent with 100% filtration rate. For this really, really tiny mass of this copper-based filter, it's 18 grams of this filter compared to kilograms that are commonly used in liquid argon TPCs. So it's very surprising that we can get this high of an efficiency, but it's worth saying that it's at this kind of low speed with regard to the design of Xenon Enton. For the non-evaporable getter, we get a lower efficiency, 60%, but again, this is a lower background emanating filter. So then this guided the design of this is a picture of the liquid xenon purification system in Xenon Enton. And this design was guided by these outcomes. And we were able to do nice commissioning tests, kind of equivalent tests in Xenon Enton with the filters, with the filters from Columbia. And we found that since the flow is 10 to 20 times higher in Xenon Enton, you correspond to the efficiency begins to drop. The constant seems to be the efficiency as a function of the time in contact with the material. So that means we had to increase the mass of the filters to correspond to this increase in flow. That made this copper-based filter untenable in terms of radon. So what we did was this kind of 2-pronged approach. We start by cleaning the xenon very rapidly with a high radon emanating but 100% efficiency copper-based filter, and then switch to this low radon emanating filter that has a lower efficiency but a sufficient efficiency to achieve very high lifetimes. And this is the demonstrated lifetime after only several days of operation. We're higher than that now, which is several milliseconds and better than any of our previous TPCs. Yeah, so just finishing up, we were able to do this. The one thing I would highlight that I think is interesting and not obvious is that this distillation effect, this interphase exchange removal, is kind of in our little test stand was kind of within a factor of 10 of the outgassing or the desorption in Xenon Enton. So you could think about, can you make a radon-free purification method that just relies on this distillation effect with a larger area and some kind of enhancement in the gas phase. Just by cleaning gas above a liquid, you can remove oxygen at a high rate. Yeah, so that's all I have to say. Thanks for listening.
Thank you, Joey. Any questions? If no, maybe I just have a quick one. How does that oxygen injector work? Like, how do you know exactly how much oxygen you're injecting?
Yeah, so what we did was just a calibration. I mean, you can estimate the permeability of this silicone is well known, and we designed the thickness to be able to inject 1 milligram per day, up to 1 milligram per day. Basically, you have you put a same pressure, equal pressure of xenon on either side, and then you add a partial pressure of oxygen with a leak valve. And we did that for several values, and in vacuum measured the permeation rate with just oxygen across. So then that validated this calibration, then we use that to scale subsequent measurements.
Okay, cool. Thanks a lot. All right, thank you, Joey. We can go to the next speaker, which is it Gregor? Is that how you say your first name? About the purification of the liquid argon in Legend. Please go ahead.
Yes, so can you see my slides?
Yes, there's like a Microsoft Office thing. Yep.
Yep.
And we hear you well. Go ahead. Thank you.
Okay, so I will talk about the purification of liquid argon for the Legend 200 experiment. So this is the outline of my presentation. So after a few words of about the motivation of this research, I will present the design and performance of this purification which we have built. And then I will also show you, of course, the result of the purification campaign. And at the end, the summaries. Sorry. So Legend 200 is designed essentially to search for neutrinoless double beta decaying germanium-76, and the detector is under construction in Hall A of the Gran Sasso underground laboratory. And what you see on this plot is essentially the discovery sensitivity in years as a function of the exposure, given in ton years, and also as a function of the background level in the experiment. So this is represented by these different curves. And of course, in order to get the maximum sensitivity, you should be background free. And this is possible. We have proven this essentially within the Gerda experiment. So what are the background reduction techniques in Legend 200 or other similar experiments? So of course, the detector must be located deep underground. So the residual muons are rejected by the muon veto, and the external background, external, I mean external to the, with respect to the germanium detectors, which are our source of neutrinoless double beta or neutrino double beta decay. In order to reject this external background, we apply the liquid argon veto. So liquid argon serves in our case as a cooling medium for the detector, passive veto, passive shield, and also as an active shield. And then you can use also detector anti-coincidence and the pulse shape discrimination. So we focus here on the liquid argon veto. And this was essentially discussed in details by Stefan Schönert on Wednesday, so you can check his presentation. I just wanted to say that essentially this liquid argon veto is composing of germanium detectors, which are placed somehow between two barrels formed by wavelength shifting fibers. So if you want to check the details, please go to the presentation by Stefan. And now the question is, of course, what are the conditions to have very efficient liquid argon veto? So clearly you need pure liquid argon. So then you get a high light yield, and then you get also decent attenuation length. So you can see, for example, energy depositions which are taking place relatively far from your instrumentation. So another parameter which is related to the purity is the triplet lifetime, which is essentially a lifetime of an excited state, triplet excited states. So gives you a time when the excited argon deexcitate essentially. So what does the very pure argon mean in terms of impurity concentration? So if you look at this table here, we have a specification for different commercially available qualities. And then if we look at the argon 6.0, then you can see, for example, that specification for nitrogen, oxygen, and water says that they should be all below 0.5 ppm. So what does it mean 0.5 ppm in terms of triplet lifetime, for example? You can look into the literature and check, for example, the work paper. So if you take 0.5 ppm oxygen, this means that you expect the triplet lifetime to be at the level of 0.9 microsecond. Yeah, and in the best case, you expect something like 1.3. So it means that in the worst case, the best available commercial quality, like 6.0 argon, may be not good enough if you want to have a good scintillation properties. That's why essentially you need a purification method. So what are the requirements for our purification system? So we have to take into account that the Legend Cryostat capacity is 91 tons. So we need clearly purification of argon in the liquid phase. And the system is optimized for removal of oxygen and water, because oxygen and water are essentially affecting the scintillation properties at most. And we assume also that our initial concentration in the gas for oxygen, nitrogen, and water will be at the level of 1 ppm. So this was somehow worked out with Linde, that they will deliver us the so-called Legend 200 argon quality. So if you look at the specification, this is something between 5.5 and 6.0. And every delivery should be somehow confirmed by a dedicated certificate saying that this gas which they deliver has really lower concentration than 1 ppm with respect to nitrogen, oxygen, and water. So then the system is placed between the storage tank, liquid argon storage tank, and the cryostat. So we are purifying liquid argon during filling of the cryostat. And we assume that in one go, we should purify at least 8 tons of liquid argon, which is essentially the capacity of the liquid argon storage tank. And during the purification or during the filling, we monitor continuously the quality of the liquid argon using, for example, this LAMA instrument, which was also described by Stefan, which is installed directly in the cryostat. So this is the schematic view of this purification system. So we have essentially 2 units, which are almost identical. One is optimized to remove water, the other is optimized to remove oxygen, as essentially each unit consists of 2 traps which are placed in a vacuum insulated in a vacuum vessel, which provides thermal insulation. So the water traps are filled with molecular sieve. Every trap contains 4 kilograms of 4 angstrom molecular sieve, and the oxygen traps, they are filled with copper catalyst. So this copper catalyst chemically binds oxygen, and then copper oxide is formed. And then in order to regenerate this, so you have to reduce this copper oxide. So at high temperature, you essentially flush these traps with hydrogen. So in our case, we use hydrogen-nitrogen mixture, so 5% hydrogen in nitrogen. And the regeneration of the molecular sieve is relatively easy because you just heat it and pump to high vacuum for some time. Okay, in order to verify that the performance of the purification system, we have 2 additional instruments. One is the so-called gas analyzer. So this is essentially, these are essentially 2 commercial instruments which are able to measure nitrogen, oxygen, and water down to 0.1 ppm. And then we have the scintillation analyzer, which is essentially based on 2 photomultipliers installed in a 60-liter metal seed dewar. So you can fill this dewar directly with liquid argon and then measure the, for example, the triplet lifetime directly. Okay, so after designing and completing all the parts, the system was assembled and initially tested in Munich at the Technical University. So you see the system here on the left. So behind this control cabinet, you see the module, which is optimized for water removal, and the second module, which is optimized for the oxygen removal. And you can see that this is everything, that this is relatively compact and installed essentially on a Euro pallet. So this was also our goal, to have it relatively small. And then, as I said, we also did first tests in Munich. So you can see on the right picture, so the system during purification of the liquid argon 5.0 delivered in this 600-liter tank. And for the initial test, we used argon 5.0 with deliberately higher nitrogen and oxygen concentrations. So we had 4 ppm nitrogen and 2 ppm oxygen. We verified this with our gas analyzer. We additionally measured water at the level of 0.3 ppm, and also the triplet lifetime with this scintillation analyzer, which was 0.6 microsecond. And this is something expected if you take into account these impurity concentrations. Yeah. So then we purified about 1 ton of this gas, and we filled the SCARF cryostat. The SCARF cryostat is a copper cryostat used by the Munich group to test the germanium detectors, also the components of the liquid argon VITO. So if you want to see the details, you can go to the talk of Christoph Vogel, which was also given on Wednesday, and check how it looks like. And then after the purification, the quality of the liquid argon filled into the SCARF cryostat was measured again. The triplet lifetime with another LAMA system. This is another LAMA system. So you can see the plot here. And the measurement gave 1.3 microseconds. So we went from 0.6 to 1.3 microseconds. So we proved essentially that the system works very nicely. So remove oxygen, nitrogen, and water. And also, I mean, we didn't assume that it will remove nitrogen, but as you can see, to some extent, we can also reduce the nitrogen concentration. Okay, so this was in May, in March this year. So after the test in Munich, we sent this system to Gran Sasso, to LNGS. And you can see the system here placed behind the liquid argon storage tank and also the liquid nitrogen storage tank. So in May, essentially the purification system was integrated with the cryostat cryogenic system and commissioned. So we did some run tests, sending some liquid argon into the cryostat. And essentially we started the filling in June this year. So at the beginning, the cryostat was, of course, warm because this is a huge tank, 65 cubic meters volume. So you need to cool it down. For this, you need several tons of liquid argon. And we decided to use this so-called cool down phase, essentially to measure the breakthrough, the so-called breakthrough curve for this purification system. So in other words, we wanted to see how much argon we can produce purify until the regeneration is needed. So this is shown on this plot. So here on the horizontal axis, you see the liquid argon mass processed, and here on the vertical axis, you can see the measured triplet lifetime with this scintillation analyzer. So you can see that up to 10 tons, the triplet lifetime was in the range of 1.3 microseconds. So we had very good quality of liquid argon. Then between 10 and 12 tons, it drops a little bit to 1.2 microseconds. And then after 13 tons, we have slightly above 1.1 microsecond. So to compare, we have the average value here also for the unpurified gas. Yeah, so this is something like 0.9 microseconds. So in our case, we decided that we have to regenerate the system after processing 12 tons. And okay, and then after the cryostat was called, we started the filling, and you can see here the data from Llama. So we work continuously 24 hours a day, 7 days a week. And this period here displayed corresponds to 3 weeks. So in the upper plot, you see the measured triplet lifetime. This is the triplet lifetime measured directly for the liquid argon filled into the cryostat. So after this 3 weeks, we had something like 65 cubic meters of liquid nitrogen of liquid argon in the cryostat. So this corresponds to about 70% of the total volume. So you see that the average value is at the level of 1.3. And then here we have also the light yield produced by Llama. So this is essentially number of photoelectrons for 60 kV gammas. So this was very nice. And then essentially the last batch, which was delivered by Linde, was somehow contaminated with nitrogen. And of course, we didn't know. We just realized observing this triplet lifetime and the light yield. So you can see that both values drop significantly. And you can see the zoom, for example, here to this light yield. You see that this was continuously dropping. So after a while, we stopped when we realized that something is wrong. Yeah. So next weeks or next months, we essentially spent to investigate together with Linde the issue. So why the nitrogen, or why the argon was contaminated with nitrogen, although the certificate was essentially fine. In the meantime, we of course continued to monitor the quality of the liquid argon in the cryostat, and you can see that the triplet lifetime is practically constant at the level of 1.1 microsecond. The light yield is dropping down a little bit, but this is a very little change. If you look on the scale here, this corresponds to about 1%. Although there were several operations on the cryostat done because we had several test immersions of different instrumentation. So for example, these are these gaps here where we, when it was necessary to switch off this Llama system. And then at the beginning of this week, we started to, we restarted the filling process essentially. And you can see that this light yield is starting to rise a little bit because we still have to add something like 25 tons. Then we hope essentially that we can dilute a little bit this argon, which is already in the cryostat, and recover a little bit the initial purity. Of course, we will not go back to this 1.3 microsecond, but maybe 1.15 or something like this. Okay, so this brings me to the conclusion. So, so our liquid argon purification system allows us to obtain liquid argon of very high purity. So we have to regenerate the system after processing 12 tons of liquid argon. About 65 tons of liquid argon was purified and filled into the Legend cryostat, and this argon was very pure. The average value for the triplet lifetime was 1.3 microseconds. The average filling rate was 350 kilograms. Then unfortunately, we had this problem with the high nitrogen content in the argon. It was at the level of 10 ppm, so clearly the certificate was faulty. And then thanks to this online monitoring with Llama, we were able to interrupt this timing, although the triplet dropped already to 1.1 microsecond. So we recently restarted the filling, and we plan also in the future somehow to purify this liquid argon in a loop mode. So we have a dedicated cryogenic pump installed already on the bottom of the cryostat. So we installed it before we started the filling, of course. So we want to pump this argon outside out of the cryostat and send it through this purification system and then back to the cryostat. So we could perform this loop purification. So hopefully we can fully recover the purity of liquid argon. Okay, thank you very much. That's all.
Thank you, Gregor. We have a question from Leo.
Can you estimate what's the effect of going from 1.3 to 1.1 on the overall background budget of the experiment?
So this is not related to the background, because we wanted to have as good as possible the scintillation properties in order to identify or reject the background. Yeah? So I don't know exactly, so nobody knows what is the specification. Yeah? So we will see when we start the experiment, let's say if this 1.1 is sufficient, if the liquid argon is sufficient at this level or not, or we have to additionally purify, then we have this option to purify the liquid argon in the loop mode. Yeah.
Okay, thank you. We have to move on to the next talk. Thanks for the nice talk, Gregor. So next we have Akko about the electron lifetime in Nexo modeling.
Okay,
we see
I hope you can see. Okay, great. So yeah, thank you everyone. I'll be talking about modeling the effects that impurities have on the electron lifetime. This is specifically done in the context of Nexo, but can be applied to any other large liquid Xenon TPC. So like I said, this is done within Nexo, and Nexo is a next generation experiment looking forward in neutrino double beta decay at the ton scale. And so I'll just go briefly over a couple of the key features that may be relevant for this presentation. So Nexo is going to operate as a single phase time projection chamber. We're going to fill it with 5 tons of liquid xenon enriched in xenon 136. And the experiment has a monolithic design with a single drift volume of roughly 1.2 meters, which you can see here on the right side. And the energy resolution of the experiment is estimated to be 0.8% at the Q value. And the goal for Nexo is to reach an electron lifetime of about 10 milliseconds. And so if you want to hear about more details of Nexo in terms of its physics reach and some of the other instrumentation we're doing, there were a couple of other talks on Nexo at LIDINE over the last week. And then at the same time, we also have a pre-conceptual design report on the archive, as well as the recently published sensitivity paper for more details. So why care about the electron lifetime this much? So Joseph already gave us a pretty nice overview, but let me just reiterate. When events happen in a liquid xenon TPC, we get a scintillation signal as well as ionization charge, and we drift this charge over a long drift distance to an anode plane for collection. In Nexo, this is the drift length that's now increased to 1.2 meters compared to its predecessor, XO200, where we only had 20 centimeters of drift length. And so if you have a charge cloud that's drifted at a location to the anode, along the way, you have impurities that will capture some of the electrons and will reduce your charge signal. And in order to accurately estimate the energy, you of course have to correct for this electron lifetime effect. And even though you calibrate the detector, there is some residual systematic errors due to temporal or spatial variations. And these systematic errors matter less in a relative sense if your electron lifetime is just longer. So it will have a less effect on the energy resolution. And so the way to improve the electron lifetime, obviously, is to reduce the concentration of those electronegative impurities. And this is the relation by which the electron lifetime is related to the impurity concentration. And then the other thing that comes into effect here is the electron attachment cross-section, basically the likelihood of an electron actually being grabbed onto by an electronegative impurity. So like I said, for Nexo, the goal is achieving something like 10 milliseconds of electron lifetime. And so the way we want to approach this is by developing a model that takes into account the many sources of impurities that are possible in such a detector. And the motivation for this is twofold. One is that we want to be able to qualify materials the same way we do it for radioassaying materials in terms of their radio purity. We wanted to do the same thing in terms of their chemical purity for xenon. And then once we have all these, once we have this model in place and we know, and we have a detector design, then this model would be predictive of what the expected electron lifetime of such a detector is. And so on the right side here, I have a cartoonish schematic of Nexo, where we have the TPC, we have a purification line with the purifier up top with the efficiency eta and a flow rate F. And then there are certain processes that will introduce impurities into your liquid. One is desorption of surfaces that the vessel is made of. Then there are materials that you're using to build the field cage or your reflector of, typically plastics. So there's some addition of impurities through diffusion. And then there's also impurities that are introduced in the gas phase that they will slowly dissolve into the liquid phase. So in order to quantify or to come up with this predictive model, we need to measure certain input parameters that need to be measured experimentally. So one is the intrinsic outgassing rate of those materials, like what is the desorption rate of certain types of metals at liquid xenon temperature? What is the outgassing rate of plastics at liquid xenon temperatures for different species of gases? And then the other thing that we need is what's the concentration, the ratio of the concentration of those species in the gas and the liquid phase, usually given by the Henry's coefficient that needs to be measured. And then the final piece is the electron attachment cross-section that I mentioned on the previous slide, which usually relies on measurements from the 80s that we would like to repeat and make sure that that they're actually accurate. And so the question that we're asking ourselves is, given a certain purification system, how large of an outgassing rate is actually tolerable while still maintaining an electron lifetime of 10 milliseconds? And so to address the first bullet point here, we have built a room temperature outgassing setup that is supposed to measure the outgassing rate of materials such as plastics. So the way this works is that when the plastic sits in atmosphere, some of those gases will dissolve into the material, and then once you put them into a vacuum chamber, they'll be released. And so the way you come up with a model is by you solve the differential equation, which is the diffusion equation for certain boundary conditions. In this case, for instance, for a slab of thickness D, and then you get the outgassing rate that can be in a simplified version written like here. And so D is the diffusion constant, which is also temperature dependent and is usually given by this Arrhenius-like equation here. And so what the setup basically does is it measures the partial pressure of different gas species emitted from the sample as a function of time and temperature using a residual gas analyzer. And then at the bottom right here, what I'm showing is an example data set that we acquire where on the y-axis, you have the oxygen partial pressure in millibar, and then on the x-axis, the time since we started the measurement. And then so the black data points, the black points are the data, and then the red line here is the fit corresponding to this function over here. And then through fits like these, we can extract the relevant parameters, D naught, the activation energy at infinite temperature, as well as the activation energy, and then relate these to the outgassing rate at the liquid xenon temperature. And so we did a little bit of literature search and looked at what other people have measured for different types of plastics, elastomers, and polymers. And so these blue data points is what we found in the literature. And then this is a power law fit to this data. And these are other different colored data points here are the samples that we measured in our setup, which contains Teflon, acrylic, epoxy, and Vespol. And all of these different types of plastics seem to be following this relatively simple power law. So we're currently working on reducing our systematics, which we think are mainly due to us not fully understanding the temperature of the sample. So the other two components for this model, the Henry's coefficient and the electron attachment cross-section, can usually be measured by a liquid purity monitor. So this is something that we have also built here in our lab. And for many experiments, it's many experiments that have a finite electron lifetime, like xenon, like XO200, it's not exactly clear what the impurity source is that it's limiting the electron lifetime. So with our setup, we would like to measure this, and for that, we need in situ measurements. And so what we want to measure is not only the outgassing process that is responsible for the lifetime that we're measuring, but also what type of species is responsible for that. And the key parameters of our purity system is the purity monitor is that we have no plastics, so we have low intrinsic outgassing. We have continuous purification through a SAS getter. And then we also have a cold trap enhanced RGA system, which allows us to measure impurity concentrations down to 100 ppt. And we've consistently been able to measure lifetimes greater than 1 millisecond. And we've done some consistency checks against EXO 200 data, and we believe we understand our system reasonably well. But otherwise, the design is pretty much similar to other purity monitors. So this is a photo of what this looks like. So one of the first things that we have done is measuring the Henry's coefficient of oxygen in liquid xenon. And so here I'm just showing a very simplified cartoonish procedure that we did. So we have a oxygen bottle that's attached to the system through a calibrated leak valve. And so we're filling a known amount of impurities into the system, into our liquid xenon chamber here. And then we are slowly filling the chamber with a known amount of xenon through a certain level, and then wait for equilibrium to kick in, and then measure the impurity concentration in the gas phase above the liquid level through our cold trap enhanced RGA. Then we fill more xenon and repeat the measurement over and over again. And the expectation is that as you have more liquid present in your chamber, some of the impurities in the gas phase will slowly dissolve into liquid, lowering the concentration in the gas phase. And so we've done a couple of different liquefaction runs and some systematic studies, and we've established a Henry's coefficient measurement of oxygen in liquid xenon of roughly 60. And interestingly enough, this seems to be agreeing reasonably well with the simple ideal gas behavior. So if you just take, for instance, the ratio of the partial pressures of like oxygen and xenon at the xenon, at the liquid xenon temperature, you exactly get something on the order of like 60. So the plan for the system is now to actually measure the Henry's coefficient for some of the other species as well, like water, this should be water, not hydrogen, carbon dioxide, and also nitrogen. So in summary, we're planning on building this model that will be needed for big noble liquid detectors to quantify how impurities are added and removed from these experiments. And the motivation is twofold. One, qualifying potential materials that can be used in these types of detectors, but also once the detector design has been made, then predict what the achievable lifetime for these kinds of detectors can be. And some of these parameters need to be experimentally measured. And so in this talk, I've outlined how we were going after the first two parameters, and then the last parameter, the electron attachment cross-section measurements, these are currently underway. And while this whole thing was done within the framework of Nexo, these kinds of measurements are equally interesting for other large noble liquid detectors. So thank you for your attention, and I'll leave you with a photo of our most recent collaboration meeting.
Thank you, Akko. We have a question from Florian.
Yeah, hi, thanks for the very interesting talk. I just wanted to ask, do you expect some correlation from the medium of the liquid xenon on the outgassing? So because there was some discussions about the polarity of the xenon and that it could dissolve impurities from surfaces. There might be some difference from testing at the temperature of liquid xenon or in the medium. So I just wanted to know if you could comment on that.
Yeah, so the model that we want to develop, basically, the goal we want to achieve is whether we can measure those samples in a relatively simple room temperature outgassing setup and extrapolate those numbers to liquid xenon temperatures, and that is good enough. And then we'll obviously cross-check these measurements in situ in liquid xenon. If there's a one-to-one correspondence between these two, then obviously we will not measure all of these samples in liquid xenon, but then rely on these room temperature outgassing measurements.
Okay, thanks.
Another question from Joey.
Yeah, nice talk, thanks. I didn't get in the room temperature outgassing system how you vary the temperature to get the activation energy.
Yeah, so I didn't mention it here, but at the bottom of this flange here, we have a thermoelectric cooler attached that can either cool or heat up the chamber. So, and then we have two thermocouples attached to the sample on the top and the bottom, so we can monitor the temperature as we increase the temperature through the TC.
Thanks.
Thank you, Akko. Let's move on to the next talk. It's Pablo talking about underground argon radio purity.
Hello, I'm sharing my desktop.
Yep, we can see it.
You can see it, right? So hello, everyone. I'm going to switch on the chronometer to avoid going too far in time. My name is Pablo García. I work in a CIMAT in Madrid, Spain, which is a research institute. And I'm going to talk about the measurement of the underground argon radio purity for dark matter data searches on behalf of the DarkSide collaboration. So, just let me set the stage in. Well, it's very obvious to all of us that in the direct search for dark matter, Xenon experiments rule. I mean, they have the highest sensitivity, in particular for highest masses. But still, argon experiments are competitive or should be competitive if they use a high target mass and low background. And the usual limitation is the intrinsic activity of the radioactive isotope argon-39 in atmospheric argon. Due to that, the future argon-based experiments, in particular DarkSide 20K and Argo, will use argon extracted from underground wells because they have a reduced argon-39 activity. This goes without saying that this is a cosmogenic isotope, so in the underground wells, the gases are deprived from this radioactive isotope. So DART is a small experiment, which is a sub-project of DarkSide. And the goals of these experiments will be first to perform a measurement of the concentration of argon-39 in underground argon. This is a physics measurement interesting in itself, but also continuously determining the purity of argon, not only in terms of argon-39, but other isotopes and impurities for each underground argon batch that will be delivered to the DarkSide experiment for operation. So putting it in a more graphical way, this is the usual graph with the dark matter nucleon interaction cross-section versus the WIMP mass. And as you see clearly in the high mass part, xenon is really with the highest sensitivity. In the low mass, the still DarkSide has sensitivity, but this is a different issue. So the strategy of the experiment DarkSide is to have a large exposure, which is 200 ton year, with a strong background rejection, especially those from electron recoils. And this is where the argon-39 enters. So as I said, argon-39 is a naturally occurring beta-emitting isotope. The Q value is 565 keV, which is right in the region of interest for dark matter searches. And as I mentioned, the atmospheric argon has an activity which is 1 becquerel per kilogram. So for 20 ton, in fact, is 50 argon tons in the experiment. This is a huge rate. That's why we plan to use this underground argon that was used for the first time in the DarkSide 50 experiment. And there we measure an activity of 0.73 millibecquerel, which is 1400 depletion factor with respect to atmospheric argon. So if we assume that the atmospheric, the underground argon will have a depletion factor of 1400 as we measure in DarkSide, we expect like 10 to the 10 electron recoil events in this exposure of the experiment. So pole shape discrimination is crucial in the analysis, and the deep 3600 experiment already proved that they can achieve a reduction of 10 to the 8 events per keV, reaching a level of 0.2 events for 3 ton year exposure in the region of interest. Okay, DarkSide is a completely different experiment, so we expect to achieve even highest reduction factor with the pole shape discrimination. As I said, I mean, just with underground argon, without further purification in terms of argon-39 DarkSide, physics goals are at reach. So for extracting and processing the underground argon, we will use several facilities. One is Urania, I will describe in the next slide, then area. And I underline once more that for us it's crucial to measure the depletion factor, not once in a time, but for all the different batches delivered to the experiment in case that some air leak occur as we suspect it happening in dark side. We have some complementary measurements that point to an R leak in the dark side, 50 underground argon. So we expect even higher depletion factors. So the argon will be extracted from the underground wells in Colorado, in the Kinder Morgan facility, and this is a CO2 commercial plant, and the capability for underground argon is like 330 kilograms per day, which goes up to 90 tons per year. Then it will be shipped to area in Sardinia, in Italy, where it will be passed through the 350-meter tall cryogenic distillation column to be purified and to isotopically separate argon from other elements. So we get in dark side 20K detector grade argon. And the argon will go from there to the LNGS for the operation on dark side. But small bottles for each batch of argon coming from Irania will go to Spain, to the laboratory of Canfranc, underground laboratory of Canfranc, where the dark detector is placed, where we will measure the argon 39 depression factor. So area is, as I said, is a plant that hosts 350-meter cryogenic column, as I said, and is designed to reduce the isotopic abundance of argon 39. And as we had recently published the first results of the operation of the first module of the tower, which is not 350 meters, but 26 meter tall, I showed this graph, which is the separation of this 29 nitrogen-2 isotope with respect to 28 nitrogen-2 isotope, in which if a 30% separation in matter of few hours, just with a single module. And this is just a test proof of the concept of the area facility. And I underline this publication from earlier this year, with all the details. So DART in RDM is the name of this, let's say, small experiment that is fully described in this GINST article from 2020. I describe here. As I said, with why we have this particular detector, because in atmospheric argon, 1 becquerel per kilogram contamination corresponds to about 10 to the minus 15 grams of argon 39 per gram of argon, which is a tiny amount, and we cannot use the traditional methods for screening the argon. So we built this chamber. This is a small low background detector designed to measure this depression factor specifically, and it is made of 99.98% oxygen-free high conductivity copper cylinder with more or less 1.4 liter active volume and acrylic support structure that is coated with TPB, and the readout on top and bottom is performed by 2 PDMs with each is 1 centimeter square silicon PMs. And these silicon PMs are from the main production of the dark side 20K experiment. They are called RIs. So the main backgrounds are the gammas, the external background from the surrounding rock, and the internal background from the material. So we perform an extensive screening campaign for the materials and the components of DART detector. So currently DART is located at the LSC, the Laboratorio Subterráneo de Canfranc, under 1400 meter water equivalents, and it will be installed inside RDM, which is let's say a previously existing dark matter experiment. It is a liquid argon TPC with a volume that is a bit less than 1 ton of atmospheric argon. It will be used as veto against the backgrounds, essentially the gamma background. So some pictures on the left, you see the copper chamber hanging from the flange of the cryostat. This was done at CIEMAT in Madrid. It was built in Madrid with parts from different institutes, Carleton University, and INF and Cagliari, and University of Cagliari, and some other institutes. And in the middle, you can see it already inside the cryostat, and the basement is a lead brick castle being built. On the right, you can see the full detector mounted with a full lead castle and surrounded by a plastic cover so we can flash radon-free air. So for the operation of this experiment in the future, we will use, of course, RDM, but in the moment, this is in commissioning phase, and this cryostat we're using for the cryonics or liquid nitrogen with a bit over pressure to keep the argon liquid and not freezing it. Okay, so let me show you 2 events from DART. in the horizontal axis, you have time in nanoseconds. In the vertical axis is the pulse height in ADC counts. And you see clearly how different they are, the alpha decay in the top and the beta decay in the bottom. And we will use these characteristic shapes to perform pulse shape discrimination. It's very significant that the triplet lifetime is very long. It's 1200 nanosecond because of the slower silicon PM response, but still we can perform efficient pulse shape discrimination, defining the well-known F-prompt variable. Instead of the usual F60 or F90, we define the F640 nanoseconds. So we integrate the signal in the 640 nanosecond for defining the fast component of the pulse. So if we plot this pulse shape discrimination variable F640 in the vertical axis here in the next slide, with respect to the integrated charge in the horizontal axis, you can see this very nice graph that was taken in Madrid on surface. As I said, is without BITO and without shielding. And you see very clear parts. I'm not sure you see my cursor here. You see this horizontal band, which is due to the cosmic means, and then the low energy, and in the middle of the F prompt, the beta decays and gamma rays. And we have this blob here in the also rather lowish energy, but higher F prompt, which are the alpha decays. If we isolate these alpha decays and do a one-dimensional plot, it's what you see on the right part of the slide. And then you see clearly the peaks from the radium-222 and polonium-218, and the peak from polonium-214. If we apply time coincidences to identify the BIPO decays, the BIPO, decays, we clearly isolate the polonium-214, and we use that for a preliminary calibration of the detector. So if we compare how things evolve from staying in Madrid on surface and going underground in Canfranc and using the LED shielding, you see that the plot on the right is essentially the same, but much more cleaner. Obviously, there are no cosmic muons, and the gamma background is significantly reduced. So the alpha particles are more clearly visible here in this graph. Okay, so clearly the external backgrounds are significantly reduced here. If I do the one-dimensional projection of this graph, in this case as function of the energy, you see in red is the energy distribution on surface with a long tail due to the cosmics. Then in blue, you see the reduction without cosmics, but still some gamma background. But once we have the LED brick shielding, we have a much more cleaner, in which we can already start to see the argon-13 spectrum in the very low part of the spectrum. Keep in mind that at this point we are not using RDM, so we have no BITO. We still expect to reduce significantly the remaining background, and once we have the full detector mounted. But as I said, we are in the final phase of commissioning. So this is a preliminary plot. It's not published, and I insist that this is with DART not in RDM and no BITO. And you can see the energy spectrum in keV electron and the number of entries in the vertical axis. And the spectrum is clearly seen below 600 keV, I would say. And of course, there is a long tail that is due to background, to higher energies. But if we assume a rather flattish background, just to have an approximate estimate of the rate we have, and apply a threshold of 33 keV, the argon-39 rate we measure is 1 count per second. There is no uncertainty in this number because we don't claim this to be a measurement. It's just an estimate, because we know that we have a large systematic uncertainties, which are mainly dominated by background, but we also have some systematics on the efficiency and in the energy calibration. But this number is roughly within 10-15% in agreement with the existing measurements. So I go to the last slide. Again, I want to advertise the last two related publications of the dark side experiment. The first one is description of DART. The second one is ARIA. And as I said, we will have as a main goal measuring the depletion factor with DART for every batch that we are sending to the site. And we know that we are sensitive to depletion factor exceeding a factor of 10 times that reported by dark side of 50. So that means that we will reach 14,000 depletion factor. So the detectors have been validated at CMAT and Canfranc and finishing already to leave place for at least 1 or 2 questions. And that is installed already at LEC and will be fully commissioned beginning of 2022. And we plan to operate for a long time, measuring all the batches that will go to the dark side and Argo experiments. Thank you for your attention. I'm sorry for the extra time.
Thank you, Pablo Garcia. Any questions? No, then well, thank you for the nice talk. This looks promising. Well, I think we should move on to the next talk just to gain back that one. Thank you. Okay, so next is Andrew talking about the Krypton removal in LZ. We see your screen.
All right, yeah, so I will be giving an overview of the Krypton removal system for LZ that we built and operated at SLAC. So just a brief overview of LZ. It's a xenon-based dark matter direct detection experiment that's currently being developed at LEED, South Dakota, and it will have 7-ton active volume when it's complete of xenon. It's a dual phase detector, so we read out light and charge both through scintillation signals, and we can use the ratio of those signal areas to discriminate between nuclear and electron recoil backgrounds. LZ has a large amount of shielding and background rejection infrastructure for external backgrounds, including a water tank, the rock from being located about a mile underground, the self-shielding from xenon itself, and then we also have a sophisticated outer detector system that will be used for characterizing backgrounds and veto during data taking. So I'm going to be focusing on the internal backgrounds, which obviously are not able to be mitigated by the shielding. And these mainly produce electron recoil backgrounds. So as I mentioned, we are able to discriminate to some extent between electron recoils, and our signal will be nuclear recoils. But there is quite a bit of overlap between the two bands. And so we also want to minimize as much as possible the amount of electron recoil backgrounds that we're seeing. And the largest contributor in the category of internal backgrounds is xenon contaminants. And these are radioactive noble elements that are not removed from the getter during detector circulation. So the most problematic of these is radon. And I won't be discussing radon. It's got its own dedicated system in the circulation system of the detector. But our system was developed to reduce the amount of krypton in the detector. And then also kind of as a byproduct of this technique, we also reduce the amount of argon in the detector. So the reason that the krypton needs to be removed from the xenon is that it contains about 10 parts per trillion of the isotope krypton 85, which is a beta emitter. And krypton 85 has about an 11-year half-life. So we don't have the luxury of waiting for it to decay away before we start. As part of the process of extracting the xenon from the atmosphere, you capture about 5 parts per billion at the end of kind of the research grade purification process. And the LZ science goal requires that we reduce that level to less than 300 parts per quadrillion. And as I'm showing on the right here, that will make our krypton 85 background comparable to, hopefully subdominant to, the solar neutrino background. And so the way we deal with the krypton contamination is by removing it from the xenon before sending it to SURF for deployment in the detector. And we use a technique called gas charcoal chromatography, where the differing transit times of different species of gases through charcoal allow them to be separated based on when you sample that stream. And so because the gases adsorb onto the charcoal based on their polarization, the more polarizable the atom is, the longer it will spend adsorbed onto the charcoal. And so this means that any of the noble elements that are lighter than xenon, which are less polarizable, will be removed from the column faster than xenon. And so our main focus is krypton because that's the largest contributor, but this also explains why we get a large amount of argon reduction as well based on this process. So this is kind of a cartoon overview of our system at SLAC. It consists of three main phases. We have the chromatography loop where we feed in the xenon, and then as we circulate through the column, the krypton emerges from the column and is trapped in a cold trap at liquid nitrogen temperatures, and that will later be discarded. Once the krypton has all been removed and we start seeing the xenon emerge from the column, we switch to the recovery process where the xenon is flowed in a loop through this freezer at liquid nitrogen temperatures. And so the xenon is captured in the freezer and stored there while the helium is allowed to exit and continue circulation. And then finally, when the freezer has reached its full capacity, which is about 200 to 300 kilograms, we warm it up into gas phase and compress it into storage cylinders, which will be transported to Surf and South Dakota. This is a photograph of our system. Not all of the parts are visible and it's very busy, but you can kind of see the scale and the complexity of the system. And one thing to note here is that we actually have two charcoal columns, which I did not show in the cartoon. And this allows us to process in parallel where if one column is currently in the chromatography loop, the other column can be recovering the purified xenon, and then we can switch back and forth. And that allows us to just maximize our processing rate rather than having to wait for each cycle to finish. So I'll just give a little bit of an overview of each subsystem in a little bit more detail. Each charcoal column has about 400 kilograms of activated charcoal. And we circulate at a pressure of about 1.3 to 1.4 bar of helium. And that's a flow rate of about 600 SLPM. And so for every chromatography cycle, we are able to process about 16 kilograms at a time. We kind of vary and tune that based on different parameters that affect the transit time, mainly temperature. And we tune it to have a duration of about 3 hours per chromatography cycle. And then one of the most important parts of the chromatography loop is detecting the right time to end chromatography circulation, because if you end it too soon, you may trap krypton in your column and contaminate the already purified xenon. And if you end it too late, you end up dumping xenon into your cold trap and causing clogs and all sorts of other problems. So we have two different instruments that we use for this. We have the Rga Residual Gas Analyzer and a binary gas analyzer as well. And the binary gas analyzer is tuned to measure the percent of xenon by mass in helium. And it does this by measuring the speed of sound through the gas mixture. And so on the right, there is a plot of a full trace of the BGA through one chromatography cycle. And you can see actually in this plot that you can see the krypton signal as it exits the column before the xenon comes out. Normally we can't see the signal, but this was, we spiked this xenon with krypton for calibration purposes, and it let us see this nice krypton peak in the middle of the process. Once the xenon starts exiting the column, we move on to recovery. We reduce the column pressure to about 10 millibar, which maximizes the volume flow of helium through the column and thus maximizes the recovery rate. We flow at about 150 SLPM, and we tuned recovery to take about 3 hours so that it matches well with the chromatography cycle for that parallel processing in each column. One of the unanticipated challenges that we encountered with this recovery technique is that as we freeze the xenon out of the helium stream during recovery, we do entrain helium in the xenon ice. And this is problematic because if that remains in the xenon when it's deployed in the detector, that can damage the PMTs. And so we needed to reduce the helium concentration to less than 200 parts per billion. And the technique we developed was to, once the freezer has reached capacity, to warm up that xenon and liquefy it. This releases the helium from the xenon. And then when we refreeze, the helium stays in gas form and we can just pump that away. And that gave us a result of about 10 parts per billion helium. So a really great reduction. And then once the recovery process is complete, we begin the storage process. And much of this infrastructure was developed at PSL at University of Wisconsin. And so on the left, that's our recovery compressor. And that compresses the xenon into the storage packs on the right, which are instrumented and purged and then loaded onto the truck for transport to SURF and held very securely. We also, throughout the process, mainly during recovery and after we store into the cylinders, we monitor the quantity of impurities. We use an RGA with a cold trap, and we are able to enhance the sensitivity using the cold trap from the RGA sensitivity of about a part per million down to now we're sensitive of to tens of ppq. So this gives us a really good read on whether we're meeting our specification, and also allows us to monitor purity over time to give us a look at any issues that may cause contamination before they become problematic. And this system was developed at the University of Maryland, and it's fully automated, including the LN controls and raising and lowering of the dewars. And so one of the most important aspects of this system is the automation, because we have such a large amount of xenon to process, 10 tons of xenon, 16 kilograms at a time. That takes a while. And so we need to be running the system 24/7 without human intervention. And so the two main parts of our automation system are the PLC, which we use for interlocks, anything involving xenon safety or equipment safety. And it also drives many of the lower level processes like circulation in each of the loops. And then our slope control system, we use the program called Ignition. And Ignition has an interface for Python scripting, which allows us to string together these higher level processes for long-term operations to continue cycling over multiple days without human intervention.
1 minute.
So, thanks. We developed this run control system that allows you to queue up different runs and run them in sequence. And that also keeps track of where the xenon is located from start to finish. And then the system of dynamic alarms that will notify users if anything is out of normal range based on the current state of the system. And so just to summarize, we built this large scale chromatography purification system. It purifies 16 kilograms of xenon every 3 hours, totaling 10 tons. We automated the system with Python and with our PLC, and we are on track to exceed the specifications for LZ. Finally, just to thank the LZ collaborators, many of whom did make significant contributions to the Krypton removal system. So it was really a team effort. Thank you.
Thank you, Drew. Maybe time for 1 or 2 super quick questions. If no, I had one on slide, or no, Masa, go ahead.
Just really quick. So do you have any estimation about the tritium in your system or in your LZ?
We don't, and that wasn't something that we dealt with in the Krypton removal system, but I'm not sure what our, if we have any estimates for that.
Okay, thank you.
Thanks. I had a quick one as well on I think it was slide 6. I'm not an expert on chromatography, but do you understand, like, I was just trying to understand the Krypton plot here. So I guess there's a peak of Krypton that's like dissolved in the xenon, and then there's like this baseline shift. I was wondering if you understand what's going on there.
So this plot was taken with the RGA, and RGAs can be kind of sensitive to pressure. This is also not to scale. So my guess is that the xenon pressure is actually a lot larger than the Krypton pressure. And so that shifted the baseline. I don't think it's a real Krypton signal, but just the RGA baseline changing.
Okay, cool. Thank you.
Yep.
Okay, we should go to the next speaker. It's Scott talking about crystallize solid xenon and LZ. Go ahead.
Thank you. All right. You able to see the screen?
Yep, and we hear you well.
Okay, perfect. So yeah, I'll be talking about Crystallize, which is a proposal for a future solid xenon-based dark matter detector. So we saw the first day, there's a overall discussion of the LZ dark matter detector. It's expected to greatly improve the sensitivity of these WIMP dark matter searches. But at the end of its running, around 2026 or so, even though it will improve the sensitivity by orders of magnitude, there will still be roughly an order of magnitude or so in sensitivity before we reach the ultimate limit of these detectors, which is the point at which we become limited by neutrino backgrounds from the sun. And there's still some very interesting theoretical parameter space to explore beyond this sort of second generation of detector. So the question is, once these second generation xenon experiments are over, how do we achieve that final limit, final sensitivity? And in particular, I'm going to claim that just increasing the detector size isn't really going to get us there. And the reason for that, as alluded to in his previous talk, is the internal backgrounds to these detectors. So this is a plot of projected backgrounds at the end of an LZ science run. This is shown in our typical analysis space of S1, the light signal versus the charge signal S2. We see that of about 1,100 expected backgrounds, there are roughly 800 from radon dissolved into the xenon, with another roughly 200 from neutrinos. And even after you account for the fact that there is this discrimination you can do in this space between electron and nuclear recoils, still the majority of the backgrounds, about 4 out of 6, are from this internal radon. And this is something that you can't get past by just running the detector longer or going to a bigger detector. You really have to address this radon problem head on. So one proposed solution that we're suggesting is at the end of the LZ science run, after achieving that nice sensitivity shown in the first slide, you could freeze the detector. It would be a challenge, but what you get is that after it's frozen, any radon emanated from the surfaces at the edges of the detector is now going to be excluded from the bulk of the detector. It won't diffuse through the solid crystal. So that leaves only the radon that was already present before you did the freezing. And that radon would decay away with a half-life of about 4 days, leaving only the long-lived isotopes in the chain. Now, in addition to this, we have a schematic of the radon 222 decay chain here. In crystal xenon, because all of the different daughters in this decay chain will stay at the same position, a fact which is not true in liquid xenon due to convection, you can actually use the easily identified BIPO coincidence decay to tag and remove the problematic lead-214 decay earlier on in the chain with very high efficiency. So the combination of preventing the radon from coming into the center of the detector, it decaying away, and tagging these events during the initial decay reduces the radon background so much that it's completely subdominant to other backgrounds, allowing you to reach the point where you're neutrino limited. So is it feasible to run such a detector? And the answer is yes. So solid gas two-phase TPC, we expect to perform very similarly, in fact, to a liquid gas two-phase TPC due to very similar physical properties of the two phases. I won't go into all the details, but essentially the electron mobility is roughly doubled in solid xenon for the same electric field. The electron emission is also higher. So from the condensed phase to the gas phase, it's easier to extract electrons. So this is already giving us a hint that the properties of electron movement in the solid xenon are somewhat different and more favorable in solid xenon. And in terms of the observable signals, there have been measurements from, for example, the Fermilab group indicating that there's a similar scintillation signal in solid and liquid xenon. There's also a nice poster at LIDINE in this one of the earlier sessions showing the same thing. But of course, scaling this up to something as big as multiple ton detector is a big challenge. We don't want to underplay that. So some of the challenges that we're thinking about addressing are the possibility of extra challenges with high voltage. In particular, since we're running at a lower temperature, the pressure is lower, which could make breakdown in the gas phase easier. Retaining high purity while we're doing the freezing process. So the typical circulation loop includes the bottom of the detector, which will now be frozen partway through. So purifying through the circulation could be a challenge. And then the time to freeze such a large detector and still get a high quality crystal is also something that needs to be studied. We believe, based on some work of scalability by the Fermilab group, it would take multiple months to crystallize LZ using that particular technique, which is known to be good at freezing without defects. We don't know for sure if that exact method is needed for good signal collection, however. So to start addressing some of these problems, we've built a small scale test bed at LBL. This is a typical design for a two-phase TPC, in that we have a cathode and gate forming the drift region, and then between the gate and anode is the condensed xenon level, either liquid or solid xenon, which forms the extraction region where the S2 charge signal is produced. Our particular detector is relatively small. It's about 700 grams of xenon when it's full. And we do the readout of the S1 and S2 signals with two arrays of silicon photomultipliers, 4 at the bottom and 4 at the top. So we've successfully shown operation of the two-phase TPC in both liquid and solid phases, in the sense that we consistently and reliably observe both the S1 and the S2 signal. We can be confident that we've reached the triple point, and because we can see the vapor pressure suddenly drop when the solid xenon, which we freeze from the bottom up, reaches the top of the condensed phase. And in addition to that, as I mentioned before, because the mobility is roughly doubled in solid xenon, we see the drift time of events coming from the cathode roughly half. So in particular, we've plated some polonium alphas, an alpha source, onto the cathode wires, and we see that the drift time from those events halves when we freeze. Now we can also address the question of relative scintillation signal. First, let me talk about the polonium signal. For the polonium, we see a very similar S1 size in both phases, solid and liquid, as shown in the histogram here. We also have an external cobalt source, which is an electron recoil source. It's a gamma source. And in this case, because it's not a single location, we can actually look at the dependence with Z position if we turn on the fields so that we get both the S1 and the S2. So this is a plot of the fitted mean of the S1 size as a function of Z position in both liquid and blue and solid and purple. And what we see is that there's something like a 10 to 20% difference between the liquid and solid phases. There is some Z dependence that we're still investigating, but we know that it's not, the explanation of this difference isn't due to the transparency of the xenon, because the dependence would be, for the cobalt would be in the other direction. And in addition, we don't see such a change for the polonium. So I mentioned before, there are some hints that electron properties are different in solid xenon versus liquid xenon. It's possible that part of the explanation is that there's a difference in the electron ion recombination process in solid xenon. So we did some simulations to explore this possibility, which is at this stage hypothetical. So we've simulated the bands in the S2 versus S1 space for initially the Lux detector, which is shown here. And then we've considered a hypothetical case where 15% in solid xenon, 15% of the S1 signal gets replaced by electrons. So you end up getting worse light collection, but the band means end up separating. So this is what that ends up resulting in. And the net effect is an increase in ER NR discrimination ability. So this plot of leakage fraction below the NR mean really shows an improvement of somewhere between 4 to 10 times in the WEMP region of interest. So if this were to be the case, this would, in addition to removing radon, allow further reduction of remaining electron recoil backgrounds. Then the next steps for this experiment will be an upgrade to go to more silicon photomultipliers for better light collection and better position information. Upgraded high voltage feed-throughs to get better S2 performance, and then to quantitatively study things such as the S2 size as it compares in liquid and solid xenon, the ability of radon tagging and ensuring that radon doesn't diffuse through it, among other things. So in summary, reaching the solar neutrino limit for direct detection will take work and not just scaling up existing detectors. The solid xenon TPC is a promising detector technology to address the radon background, as well as potentially other electron recoil backgrounds. And we've demonstrated at LBL that this two-phase solid xenon TPC is feasible and works with the same particle detection properties as liquid xenon. Thank you.
Thank you, Scott. Very interesting. A couple questions. First, Lior.
What do you think will happen to the electron lifetime during a few months of gradual freezing?
Yeah, so certainly if we don't have any way of circulating and purifying, the electron lifetime will get worse. So that's something that we need to address. But in principle, with a different circulation system, you might be able to avoid that issue.
Okay, if I may, just another small question. So you show that you operated at 0.74 bar. When you're thinking about actually freezing LZ, so this is more or less the level of vapor pressure you expect to have?
Yes, we want to stay relatively close to the triple point.
Yeah, otherwise your PMT will go crazy. From experience.
Yeah.
Fabrice?
Hi, yeah, hi Scott. So very nice. Actually, my question is not so much about the solid, which really looks really good, but about the silicon PM, because you quoted something that is like PhD. I was just wondering, is the number of photoelectrons that you see in liquid and gas match your expectation, accounting for the Hamamatsu efficiency?
Well, we don't have we don't have a simulation of light collection efficiency, but so I can't say with high precision that that it matches. But I will say that ballpark, it makes sense and is self-consistent. Yes.
Okay, all right. Because in some cases we have seen lower efficiency than expected, or what we think is lower efficiency.
How much lower?
Well, as low as 8% compared to the expected 24%, so a factor of 3.
Okay, I think that would probably not be consistent with our measurements.
Okay. All right, thanks.
Yeah.
One last question from Micah.
Hey, Scott, that was great. I'm sorry if you mentioned something about this, but I was just wondering how we would handle like full volume calibration of the TPC, since you can't mix in sources to the liquid anymore, and you know, like going forwards as well in time.
Yeah, that's right. That's something that we haven't really begun to address yet, but we certainly need to consider it. You could imagine some kind of source that could be long-lived that you might be able to mix in that could stay in the lattice, but that wouldn't, obviously, if it were in your WIMP search region of interest, it would add a background, so you couldn't do that. Then there's also the possibility of external calibration, though filling the whole detector volume is certainly challenging. A standard gamma calibration source probably wouldn't do it. So the subject of ongoing study, certainly.
That's the point of the fiducial volume, right?
Mm-hmm.
Okay, thank you. We should move on to the next speaker. Thanks again. So next we have Austin talking about a pulsed vacuum UV light source with adjustable intensity.
Let's see, can everybody see that?
Can
you hear me?
See it and hear you well.
Okay, good. Good. So hi everyone. My name is Austin. I'm going to talk today about this developing this pulsed VUV light source specifically for 128 nanometers, but it has some other cool features as well. It's also got some adjustable intensity, which is pretty nice. Okay, so whether you accept it or not, you probably accidentally made one of these sources fiddling around the lab, whether you were trying to make a light source or you just made some breakdown in some sort of gas or medium you were working in. So, we're going to put a spin on this general thing of making one of these light sources, and we're doing it because the groups I work with, we're trying to develop some of these more exotic photosensor work to make these very large things for liquid argon specifically, but the things could go from one noble to another. So specifically amorphous selenium is something I'm working on with Dr. Jonathan Asadi. He had a talk on Monday, and also these organic photodiodes that Mike Fabaro, one of our partners at Oak Ridge, is working on. And when you make these things, they're not it doesn't take days to make them. We can make one of these samples in a handful of hours, and then when you want to calibrate it, it's not always if you want to fill a TPC and put a source in, that takes some amount of time. You can use a xenon flash lamp, and that has a handful of issues that aren't ideal, but it'll work. And then you could use like something like a deuterium lamp, but that's a DC source, so it doesn't quite give you the pulse characteristics. And they all check some sort of boxes, but they don't check all the boxes that you would ideally like to have when you want to calibrate one of these photosensors rather quickly. So if I, just, shoot from the hip and let's say, what do we want this thing to do? Well, I mean, we would like it to go, single photon to, maybe 10,000 or so, something around there seems like a reasonable number. We want the pulse to be as fast as possible. Picosecond lasers are really cool and fun to play with, but they generally cost a decent amount of money. And, we want this thing to be semi-economical. So, nanoseconds are preferred, but microseconds we'll live with. We want to be able to change the wavelength specifically in the these liquid noble regions of interest, 120 to this 200 nanometer range, and most importantly, I want to be able to tell it when to go. I don't, it's always best when you make a measurement and it doesn't do the thing, when you're not ready. So I want to be able to say, give me light now, and it gives the light. And then we also want to make this easily integratable into whatever, existing systems we have that have, NIM logic and digitizers and all those things. We don't have to build a whole setup just to run this thing. So in order to get closer to checking all these boxes, Mike, Jonathan, and myself, started to, brainstorm and develop one. And what we ultimately came up with is this setup here that's at Oak Ridge. So we have this, we can look at this cartoon up here in the top right, where we have this vacuum pump that pumps the common lines between, 2 gas bottles and then the two volumes that we have on this source. And this thing is hooked to a monochromator, a VUV monochromator that goes, if you have a gaseous windowless source on there, it'll go from 80 nanometers, all the way up to a few hundred nanometers. So then we have this a VUV4 MPPC in there to use to directly detect the VUV light. And the way that we constructed this flash lamp is that it's got an optical attenuator built onto it. So, you can see here on the bottom, there's kind of this vacuum and gas side, and this was, there's the monochromator, the MPPC, and its little vacuum volume. And then here you can see the source with a photodiode tacked onto the back. So this was actually the first version of the source that we made, or version 0, and this was the first trip to Oak Ridge. And then we learned a whole lot on this trip, and then a whole lot that we had to make another version of the lamp and the electronics that drive it and everything, and then go back for a second run at it. But through this attenuation cavity that's built in here, we can attenuate the light to get down to these very low levels. So just kind of, more details about the device in question here is, we designed the second version to overcome a lot of the issues we had with the first one, which was this, quite often you would get these extra breakdowns, which I don't want it to do what I don't want it to do. And when it sparks randomly, that's not good. So we made the cavity much bigger for to hold the spark, but even that didn't stop the extra discharges. So we ended up coating the whole thing in Diecast 2850 with this Catalyst 11, which is chosen for the lowest outgassing of the flavors of catalyst you can get for a Diecast. So here's a cutaway from the fusion model of this drawing. So there's this back port here, which you can see down here, and you can see the 2 mag fluoride windows that are epoxied in place, and then the electrodes that are potted directly in this top assembly. So then we have this giant spark volume, and then up front there's these 2 mag fluoride windows that fit in these recesses, and there's a centimeter long gap here with this attenuation volume. And both of these ports go out to the valves up here in the top right, and this is what allow you to control the pressure and the different volumes. And then this exits out and goes into the VUV monochromator, where we can set the wavelength and perform our measurements. And you can see here, this is the one of the test versions of the driver circuitry, which I'll talk more about on the next slide. So the driver circuitry here is a little bit of a departure and kind of an interesting point of discussion. So typically, if you were going to make a flash lamp driver, you would have some sort of MOSFETs that would drive a transformer that would make a high voltage pulse, and then that would initiate a spark. I like simple, and what we ended up going with here was something to where both of these electrodes kind of float at a high voltage, and then if you pull one to ground really quickly, that'll initiate a discharge, and then it makes something that's less finicky and requires arguably less special parts to use. So this is the overview of the rough schematic. So we have some voltage filtering with some linear regulators. These things are usually powered from a nice power supply, so it probably isn't so needed, but best practices. Then the circuitry also has an integrated clock and trigger logic. So there's a set of 5.5 timers on board that have an adjustable clock to where you can go from kilohertz to millihertz trigger rates. It's got a 5.55 that's set up to take a push button. So you push a button on the external, you set it to the push button, you push it, and then it'll flash. And then it's got some AND gates, OR gates, and a buffer to kind of select between which one you want. it's kind of insensitive to the given clock. So you can even use an external one because this gets fed into a fast pulse circuit that was, this was borrowed from a linear technologies application note to where it's this quad comparator that, you can set up and generate these really fast square pulses that range from on the order from nanoseconds to hundreds of microseconds. So that's what you use as the actual spark pulse. And then that is driven to the specialized MOSFET and driver, which I'll talk about on the next slide. And the whole high voltage set is kind of here with, this handful of components that do most of the work. We have the high voltage that comes in, and there's the 2 electrodes that come out, a set of protection diodes, and a resistor that connects them to, let them charge up to the same potential. And it's worth noting that, I'll talk about that in a second. So talking about the MOSFET and the driver is, these were, the whole design was kind of based around this NCP 8107 driver and the IMW 120R MOSFET. So this MOSFET is an actual RF MOSFET. It has a 7 nanosecond spec for an 800 volt transition. And this driver is rated to, turn full on within 4 nanoseconds. So, the goal being to turn on the MOSFET as fast as possible and pull one of the electrodes to ground. So you can see in this example pulse here, so this blue is the MOSFET, and here then the purple is the trigger pulse that's sent in, and it's 100 volts per division. That's a 800 volt swing. That was quite something to set up on the bench, but it works. And then if you zoom in, you get 10-ish, 10, 12 nanoseconds for the fall time to drag that pulse all the way to ground, which is a little out of spec, but I built the circuit, so it's probably as good as it's gonna get. So we can talk about some of the results now. So the source operates in this low pressure regime. So those electrodes I showed you earlier are spaced about 2 millimeters apart. And then we keep the gas pressure and the spark volume, less than 100 torr. It depends if you're running with an RC mode, which is where you would just leave the MOSFET turned on, and that would just create a constant short. So then this would make this like a standard RC discharge that, you generally make in the lab when you want to make a spark. And the issue with this RC is it's a little finicky to set up and then keeps running stable over longer periods of time. I think when we were performing the measurements, we were letting this thing run for, 8-10 hours at a go. And you can see here, when you compare the RC versus the driver, you get a faster overall time pulse with the driver, and you get lower photon yield with the driver for the same settings on the monochromator. And here, in the driver's range, the driver works around 10 to 15 torr. And it just depends on, that a lot of that variation is just dependent on the gauge we were using and, how gently you turn the valve. But the driver likes to work in this very, weird, unstable region to where it's almost going to break down at any time. So then when you send in this pulse and drag the one electrode to ground, it initiates the spark. And, we found this to be very, surprisingly very reliable. So now that we can have, sparks on demand and it integrates in the system and runs the way we want to be able to go down to the single photon level. So we have that attenuation cell on the front. And, given our set of tools that we had at hand, P10 was the best gas to attenuate the 128 nanometers for argon. You could also use air. The cross section's like an 1.5 magnitude less. So you need a little more pressure. I think oxygen's like normally 20% abundant in air, where P10 is 10% CH4. So there's some non-trivial, fractioning going on there. But then, you could fill with air, and then the 128 nanometer light does go away. But to make the direct measurements, so, we took the one pulse and let it run, and then slowly increased the attenuator with P10 gas at a known pressure. And then you see that the photon rate falls, as you would expect, all the way down back to the MPPC noise, which we took this from the pre-trigger data from the MPPC. So, we've got something that, we can tune down to single photonish, which is very nice. One other thing is, because it's attached to a monochromator, is we can, select the wavelength. So all the measurements I showed you now were done, around 128 in argon. So this area. One of the things you'll notice when you look at this plot is there's a whole lot of gases, and that's because I could find a whole lot of gases, and it was just interesting to play with. They all have this line at 190, and they all have a few other features hidden about. And these are, we believe these are from contamination these are the atomic carbon lines that are buried in. This is from, coating everything in this epoxy. One thing to note, if you're, looking at this, with a magnifying glass, is there's nothing over here in Xenon at the 170s mark where you expect there should be something. There's 2 peaks here. It's not quite so broad. And this is because at these low of a pressures, these are all atomic lines. They're not the molecular lines. So, the mean free path here is on the order of millimeters. And, the time between like gas collisions is, many tens to hundreds of microseconds, just given some standard calculations. But we do get all the lines, all the atomic lines you expect, in the various gases. So that's quite nice. So, I'll quickly conclude that, we've developed this pulsed VUV source. It has adjustable intensity for the photons, to single photons to about 7,500 photons at 128. And when you open up the slits on the monochromator to get the full peak. Timing, I mean, you can go as fast as possible, but the full peak lasts about a microsecond with the driver. The full width is less, but you take the full peak time. The variable wavelengths, this is gas dependent, so we could try any other gas we want to get some other atomic line that we can find. But for the purposes of doing it at 128, fortunately, argon has a good atomic line there. Sorry, excuse me. The ability to trigger the source and integrate it into existing readouts, that's there. It's very easy to, it's got a synchronous output, so you can plug it directly into whatever triggering system you are, and it'll tell you when it's going to fire, and then it fires almost immediately after. And so, yeah, we plan to use this source to calibrate these organic photodiodes, as well as these amorphous selenium sensors and whatever other interesting ideas that we come up with. And, we're writing a paper about this, so you'll be on the lookout for that in the near future. And then, I want to thank everyone for your time. And if you're interested in more details about it, or you want to make one, just, shoot me an email, and, free to chat about it.
Great, thank you, Austin. Just one quick question, because we're slipping a bit on time.
No problem.
T Singh, I'm sorry, I don't know.
Yes, this is essentially the high voltage spark gap in vacuum. Actually, for your case in gas, do you see the similar effect in vacuum?
So if you pump the gas out, it stops. It stops working. If that's what you're asking.
Right. My other short question is this: usually spark gap generate quite a bit of electromagnetic noise, interfering all the electronics. I'm sure you have that case too. Is that correct?
Yeah, I mean, it generates some noise, but not, it's not like a very high powered. So there's not a whole lot of RF that goes all the way to the electronics. We do the best to ground it as properly, but it does have, there is a little bit of noise. Yeah.
Okay. Thank you, Austin. Very interesting talk. So next, we have Emma talking about fluorescence, light yield, and time constants of acrylic PMMA excited with UV light.
Okay, thanks for having me. I have changed the title a little bit. So our new title, I didn't tell you what our new title is: Light Yields of TPB and Acrylic Down to 4 Kelvin. So I was introducing myself. Hi, my name's Emma Ellingwood. I'm a PhD student at Queen's University. So today I'm going to be speaking about the results of our analysis into how the light yield of acrylic and the wavelength shifter tetraphenyl butadiene changes with temperature from around 300 Kelvin down to 4 Kelvin. So previous members of our group did spectral measurements of TPB and acrylic at various temperatures, and this was done using our optical cryostat. For this study, we wanted to take time-resolved measurements because they give some complementary information to those spectral results. In our case, our motivation in terms of materials, like our RPT acrylic sample and TPB, was that these were the vessel material and wavelength shifter used for deep. Similar measurements of these fluorescent properties of these materials are often done at room temperature, but with our optical cryostat, we can do this at a large range of temperatures to look at the trend in the light yield. So these are the spectral measurements that I mentioned. So these were presented at this conference 2 years ago, and I've included the archive link here as well for that proceedings. So these measurements were done at 4 temperatures, as you can see on these plots. But we want to expand on these results, and this was done using the time-resolved measurements that we did recently. So this study was undertaken with an application in liquid argon detectors in mind. So my examples will mainly be liquid argon related. This is the case where the liquid argon is contained within an acrylic type vessel. For liquid argon experiment, which emits light in the UV at 128 nanometers, that light cannot be detected by traditional photomultiplier tubes, which are more sensitive into the visible range. So the wavelength shifter absorbs UV light and re-emits it at wavelengths that are more compatible, or longer wavelengths that are more compatible with PMTs. So TPB is a common wavelength shifter because not only will it shift this light, but it also has a high photoluminescent quantum yield. In addition, we want to be able to identify any potential fluorescence from the acrylic, which the PMT may be sensitive to. So we have some data for acrylic as well. So the optical cryostat that we use is a closed cycle cryostat where we can screw in samples and cool them. Am I sharing screen? Yeah, okay. It didn't have the green box around it. So yeah, our optical cryostat that we use is a closed cycle cryostat where we can screw in samples and cool them to a specified temperature. The cryostat setup is meant to sort of mimic the order of events that happen in a liquid argon experiment. So when the cryostat is cooled to the desired temperature, we allow it to stabilize. The UV LED that we have emits nanosecond scale light pulses at 285 nanometers. This is just the LED that we have. This UV light interacts with the sample. If there's a coating on the acrylic substrate, then the UV light will interact with the coating first and followed by the acrylic, producing a fluorescent spectrum. The fluorescent light then passes through a broadband pass filter, which you'll see near the top of the diagram, which has a cut-on wavelength of around 375 nanometers, so that any stray UV light from the LED does not reach the PMT. It's also important to note that the trigger pulse that is sent to the circuit that produces the LED pulse is used to trigger the data acquisition system. In addition, we took the measurements from the highest temperature to the lowest to limit the amount of thermoluminescence of the sample. So just going into the samples. So first for TPB. So just to say how we process the data. So for the raw data, we just have a bunch of waveforms. And so we first subtract the baseline, so the average signal around the beginning of the waveform before the pulse. On the top right here, you see an example of an individual pulse from when the cryostat's at 300 Kelvin. A full data set at a single temperature consists of 45,000 of these individual pulses. And so on the left, you see the average pulse of these 45,000 events with the errors shown in gray. At a few temperatures for each sample, there is a noise data set taken, which is the exact same as the fluorescence pulses, except that we close the shutter between the LED and the cryo chamber. Each data pulse event is baseline and noise subtracted, and then you integrate it between bounds to get a light yield. In addition, we have done single photo electron runs, which allows us to determine integral value for a single photo electron so that we can express the integrals from, for example, TPB as a number of photoelectrons rather than just an integral. And when you calculate all those integrals, you get something like this. So this is a histogram of the integral distribution for our TPB pulses. This is fit with a skew normal distribution. And the mean of this distribution is the light yield that we use for our results. So you see for this specific run, which was taken at 300 Kelvin, the average number of photoelectrons is like 67.2. So this is the light yield we'll record for this temperature with the specific PMT high voltage settings that we have it the system set to. Overall, the average pulse intensity increases with temperature, which you can see on the top plot. One thing I also checked was whether the pulses all had the same structure, as they all looked quite similar. For this, I just divided the light yield by the integral of that pulse between the specific bounds. As it turns out, they look essentially identical on this plot. You can't tell the difference, but I promise if you zoom in, they are very, very slightly different. I'll note that the actual TPB shape could change and be shorter than the instrument response, but the instrument response could dominate what I see here. We repeated the light yield measurement and analysis at a bunch of different temperatures, or 18 different temperatures in this case, to produce a light yield curve like this as a function of temperature. I have tried to include both statistical and systematic errors. In order to compare the light yields for different samples, I would have to apply a correction to data if they were taken at different PMT high voltages. So this is a corrected data, so I can compare it later to the acrylic light yield that we found. So just to pull out some numbers, relative to 300 Kelvin, at 87 Kelvin, there's 19% more light, and at 4 Kelvin, there's 24% more light. So here's a comparison between the data we measured using our TPB-coated acrylic sample compared to a paper listed here by Franchini, which was a TPB coating evaporated on a specular reflector substrate. I've normalized both to their light yield at 300 Kelvin, and in general, you see that they do follow the same trend that the light yield increases as the temperature is decreased. So that's the TPB results. Now moving to RPT. So this specific RPT is acrylic, we call it RPT because it's from Reynolds Polymer Technologies. And this is the same acrylic that was used for DEEP, and it was a sample that we have. So this is very similar slide to what I showed for TPB, but in this case, there is no coating on top of the acrylic. And as I said, it's baseline and noise subtracted to get the light yield, and you integrate that over a range. The difference is that the RPT emits a very small amount of fluorescent light compared to TPB. So the average pulses show more of an effect from single photoelectrons. On the right, this is the baseline subtracted individual pulse, and you can see the contribution from individual photoelectrons. On the left here, I have plotted the average pulse data and the average noise, and you can see that especially at sort of lower times, that these overlay quite nicely. You can also see with the RPT pulse that there's a difference between when the shutter is open and you get the fluorescent light, which is the blue curve, and then when the noise run when the shutter is closed, and that's in orange. So for each of the 45,000 events at single temperature, the integral is described in the last slide, is calculated. So here you see the integral distribution, which looks a lot different from TPB, because here you're dealing with, as I said, single photoelectrons. So for the model we have here, the overall model is in blue. The histogram's in blue, the overall model is in black, and the dashed black curves are the different models for 0, 1, 2, or 3 photoelectrons. From that fit, you can extract the average number of photoelectrons in a distribution, which is what we use to determine the light yield. So yet again, this is the same plot as TPB, but for the RPT acrylic instead. And you see that as the temperature decreases, the overall pulse height and obviously integral gets larger. So you have a higher light yield. When you normalize the pulses to check for differences in the fluorescence with temperature, you can see yet again, they are very similar and still might be instrument response dominated. So here's the light yield for the RPT. Overall, you see a very similar trend to TPB, that as the temperature decreases, the light yield increases. You'll see that there are very small error bars, but this is because these are just the statistical errors, as I am still working on a full calculation of the systematic errors. And yet again, to pull out numbers relative to 300 Kelvin, at 87 Kelvin, you have 86% more light, and you have 121% more light at 4 Kelvin. So comparing the TPB and RPT light yields as a relative yield, matching the RPT and TPB measurements at each temperature, the RPT light yield is less than 0.5% that of TPB at the same temperature, and that decreases at higher temperatures to be even less. There was also a small additional study that I did with our normalized TPB and RPT measurements at 300 Kelvin. We took data of just the LED pulse, which we did by running the cryostat with no sample and no broadband pass filter. So this pulse should just be from the LED. Our PMT that we use actually has about a 20% quantum efficiency at the 285 nanometer wavelength of our UV LED, which makes this measurement possible. Note that the noise in the RPT pulse is because the pulse is essentially still single photoelectrons, while the light yield for the LED and TPV is a lot higher. So overall, the LED pulse is narrower than the RPT and TPV pulses, while the RPT and TPV pulses overlay quite nicely. And those two, the TPV and RPT pulses, are slightly delayed compared to just the LED pulse. So just to give an overall summary with this TPV RPT analysis, we made light yield curves using time resolved measurements from 4 Kelvin to 300 Kelvin. For both samples, the light yield increased with decreasing temperature, although the RPT light yield is much lower in comparison to TPV. And as I said before, the RPT systematics are still being evaluated to complete this analysis. And thank you for your time.
Thank you, Emma. Do we have any questions? If no, maybe just one quick one, Emma. So are you going to do different types of acrylic or just this one?
I don't think there's currently any plans to look at any other acrylic.
Okay, thanks. All right, let's move on to the next speaker then. Thank you, Emma. So next we have David talking also about wavelength shifting coatings.
Hi, thanks. Give me 1 second here. All right.
Okay, we see the slides and we hear you well.
Great. Thanks a lot. Yeah, so thanks. I'm going to be talking about the development and characterization of a slow wavelength shifting coating for background rejection in liquid argon detectors. So this is some of the work that I worked on over the course of my master's thesis at Carleton. I'm currently a PhD student at McGill University. But this is going to follow fairly closely to what Emma was just talking about. So just as a brief outline, I'm going to give a bit of motivation, why we're trying to develop this coating, talk about the background rejection using this slow wavelength shifting coating, and then go into detail of the multi-institute characterization measurements and the results and our estimated efficiency for using this technique. So the motivation, DEEP is the motivation for this is that we're developing a hardware fixed oriented solution to deal with a background component in the DEEP 3600 detector. So DEEP is a dark matter detector at Snow Lab. It ran successfully for 3 years, and we're in the process of analyzing that full data set. But one of the primary backgrounds that we had from our 1-year analysis is that radiogenic alphas occur sometimes on detector surfaces, and especially up here, as you can see in the image on the right, this is from the top of the detector, which is the inlet where the argon flows into the detector. There's very poor light collection efficiency because these surfaces are not coated in any, this is a bare acrylic. So with these, the difficulty with these is because these are alpha decays predominantly, and alphas and nuclear recoils in liquid argon in the single phase detector produce predominantly prompt scintillation light. And with the shadowing from these surfaces, you can see an illustration here. The light from that goes up into the detector is not detected and it gets absorbed by the acrylic. These alphas become artificially low energy events, and they can mimic a potential dark matter signal. So this is a currently limiting background for the dark matter sensitivity for DEEP, which is the world leading in argon. So the hypothesis is that because this is the inlet of the detector, there's mist or a liquid argon condensed film on the surfaces here, but we see some evidence for this type of behavior, and you can read more details in the reference that provided. So the solution that we came up with for dealing with this problem was to coat this inlet surface with a wavelength shifting coating that has a what we call a slow time response. So this is order 100 nanosecond time response was desired. We wanted the wavelength shift. The idea here is that the wavelength shifting coating does two things. It increases the light yield for the events that occur up in the top of the detector by shifting some of the light that would have been killed. And it also slows that light down. So this will delay the photons and affect the pulse shape of the events that occur here and shift them away from our expected dark matter signal. And we can apply pulse shape discrimination to remove these backgrounds. So you can see an illustration of what that might look like in this diagram here, where you have the non-coated pulse shape is mostly prompt with a little bit of late light, and then with the coating that we would introduce, they would have this strong intermediate component that would change the characteristic pulse shape. So in order to produce this film, there are several requirements that are desired for these types of materials. So we want, obviously, to have a cryogenically stable material, and also it to be stable in a high vacuum during deployment. There is a high vacuum in the detector. So in terms of the spectral characteristics, we want an emission wavelength spectrum measurement, and to make sure it's suitable. We want to have an understanding of the photoluminescent quantum yield, which we characterize by the ratio of incident photons to emitted photons. And we also want to know the timing structure, so the re-emission decay lifetimes for these films. And the tricky thing is that all of these properties have temperature and incident wavelength dependent effects, which means that we require measurements at 87 Kelvin and 128 nanometer incident light. So this is a technical challenge, as I'm sure some of you will be familiar with. Making measurements, detailed optical measurements at 87 Kelvin and 128 nanometer light is fairly technical. So in order to do this, we carried out a multi-institute campaign to quantify these wavelength shifting properties, and also to go into detail of most of the stuff that I'm presenting in this talk will be directly available with more details in this recently submitted paper, which you can find on the archive here. So we did production and cryogenic stability testing at Carleton University. The measurements at 87 Kelvin and 285 nanometer excitation were done at Queen's University at the setup that Emma was just talking about. And then we performed room temperature measurements at 128 nanometers at TUM. And we were able to perform some additional cryogenic 128 nanometer measurements at the Institute of Low Temperature Structure Research with AstroScent. So in terms of the production and stability, so the fluor that we first identified for this application was pyrene, which is a very well understood and long studied fluor for wavelength shifter applications. Not so much in the dark matter community, but for other applications. It has a long re-emission timescale of about order 100 nanoseconds, and this has been demonstrated and studied at cryogenic temperatures. So we had a fairly good understanding of how this would behave. The problem is that pure pyrene has a high vapor pressure, well, high for our application, and which means that we can't use it in a liquid argon detector. So the solution there is to embed the pyrene in a polymeric film, and then we can use this to create a robust wavelength shifting coating. And so in the reference, you can get the full production steps on how we actually went about producing these films. But we ended up testing several polymers to see which ones would work best. Acrylic, PVT, polystyrene, with varying concentrations of mass of pyrene. And we tested those cryogenically, and we tested them optically. So we determined that pyrene and polystyrene was the best candidate with less than 18% concentration. When you go above 18%, give or take, it starts to crystallize in the film and you start to degrade your optical characteristics. So that's kind of the maximum concentration we can have. And obviously the more fluor you have in the film, the better your efficiency for conversion is going to be. And you can kind of see on the right here, this is a couple of samples that were tested before and after being put inside of a liquid argon detector. So these were stored in a liquid argon environment for 2 months. And the polystyrene is on top, and then one of the PVT samples is on the bottom here. So polystyrene performed the best for our tests. The emission spectra and the luminescent quantum yield were measured relative to TPB samples at the Technical University of Munich. And this is done with a vacuum monochromator, the high resolution spectrometer, and a deuterium lamp source. So this is continuous light. So the yields versus TPB for these pyrene films and for different substrates were compared, and you can see an illustration of that in this plot on the right here. In blue, we have pyrene and polystyrene, which is our candidate sample for deep, which gave us the best yields at the highest wavelengths with the excimer emission, which is where the PMTs are more efficient at the higher wavelengths, where you have the strong monomer emission from the pyrene below 400 nanometers. So this pyrene and polystyrene sample, the 9%, 15% one in blue here, has a relative yield of about 46% of that at TPB, and this was measured at 128 nanometer excitation at room temperature. So as Emma actually was just giving in detail, is that they're also able to perform relative measurements using the higher wavelength, and they did that at the Queen's setup. And this was, you can read more about this with in Hisham's talk from yesterday. But we get comparable relative yield values at 87 Kelvin relative to TPB with the higher incident wavelength within 1 sigma of each other. And there's some details for the different incident wavelengths, but they're more or less consistent. And the other important characteristic for the background rejection technique is to the re-emission decay lifetime. So this was measured, and I'm not going to go into detail here, but Hisham talked about this yesterday. And we were able to measure 3 different characteristic time constants. So one that was characteristic of a monomer emission, which is 1 pyrene excited molecule decaying to the ground state, and then 2 that are characteristic of 2 different types of excimer emissions, so different molecule formation types that give the characteristically different re-emission times. But the important thing that we get out of this is that at 87 Kelvin, we're dominated by a non-monomer emission with a time constant of about 280 nanoseconds, which is suitable for our application. So it would be nice to have cryogenic measurements at 128 nanometers, and we were able to collaborate with the group at the Institute of Low Temperature Structural Research to perform similar measurements, but of the lower resolutions and with a continuous light source. So this is like DC light, and we were able to measure and confirm that we had strong emission at 128 nanometers at 87 Kelvin. There is a slight decrease in the relative yields at 128 nanometers when compared to room temperature, and this is in tension with what we measured at the higher wavelength, but there are a lot of differences in the experimental setups between the two. Also, we were able to measure the excitation curve for the films as well. The important takeaway is that we were able to demonstrate that we can get substantial yields at liquid argon wavelengths, which is critical for this application. So in order to measure or estimate the background rejection efficiency, we performed toy Monte Carlo simulations. So these simulations simulate add different components to the timing response for photons, but don't contain any reflections or photon transport simulations, just purely toy Monte Carlo style. And you can see the kind of simulated pulse shapes that come out. This is the average pulse shape of the inlet alphas. So these are these alphas from the inlet of the detector after being coated with this wavelength shifting coating with the properties that are described in the previous slides. Compared to what you would expect for a nuclear recoil like scintillation in liquid argon. And in order to estimate the background rejection efficiency that we could get with a PSD style parameter, we found an optimal window was by taking advantage of the lack of light in the inlet alphas in this prompt window. And we were able to demonstrate that we could fully separate these 2 populations of events by taking advantage of the differences in the pulse shapes. And with 100% acceptance of nuclear recoils, we're able to project all of the simulated alphas. So this order 10 to the 5 rejection power. So just in summary and some outlook, we've designed and tested this custom wavelength shifting coating that is suitable for deployment in liquid argon detectors, composed of pyrene and a polystyrene matrix. We carried out the multi-institute measurement campaign of the wavelength shifting characteristics, which included measuring relative light yields, emission time constants, the emission excitation spectra, and some temperature-dependent behavior of the films. And a preliminary simulation study suggests that order 10 to the 5 projection power obtainable through pulse shape discrimination by taking advantage of this very long 280 nanosecond emission timescale for the pyrene. So in terms of outlook, the Deep 3600 detector is being upgraded to target some of these key background components that were not addressed in the first run. And this is going to include installing this new inlet flow guide component, which has been coated in our 15% concentration pyrene and polystyrene film. So this is done. The flow guides are prepared and are on their way to Snow Lab for installation in the next coming months. We're also going to be performing full-scale Geant simulations for understanding the background rejection efficiency in the deep configuration. And that's important for future background rejection. For understanding the background rejection in the actual WIMP search. And then in addition to this, detailed optical studies are being carried out to understand things like the film thickness, refractive index, and the reflection and transmission properties, which are happening at Carleton University. And one important takeaway is that by utilizing the technique that we're describing here with these films, the activities available for how prevalent these backgrounds were in the first 1 year of data for deep, it would be possible to run the detector for about 4 years without any leakage of these backgrounds into the dark matter rejection region of interest, and with a 100% efficiency. And this would effectively eliminate this currently limiting background component in the deep detector. That's all. I'd like to thank our our funding sources for allowing this to happen, and thank you for your attention.
Thank you, David. Any quick questions from the audience? If not, so I think I might have missed this from before, but what's the timeline for the upgrades for deep?
So the plan is to start taking data again in early 2022.
Okay, nice.
Yeah. Great. Thanks.
Thank you. All right, that brings us to the last talk of the session and of the conference. So Karen talking about barium tagging and next. Okay, we see your screen.
Okay, so hello everybody, greetings from Texas. My name is Karen Navarro and I am a graduate student from the University of Texas at Arlington. And today I'm going to be talking to you all about barium tagging for the next neutronalized double beta decay program. So on Wednesday, the Arasi gave an update talk about Next. Therefore, I won't really go in detail about what Next is. I will just restate that Next operates in high pressure xenon. And so here on the lower right, you will see the energy and the tracking plane of the detector. And I just do want to mention that one of the major objectives of Next is to reduce background events. Okay, so let's talk a little bit about the sensitivity of, I'm so sorry that, there you go, okay. So let me introduce what barium tagging is for neutronalized double beta decay. So a way to reduce gamma ray background is to be able to identify the daughter barium ion made when 136 xenon decays. If we are able to identify the barium ion plus to about 1% full width half max, the energy measurement, this will give a background free experiment. So amazing. So why exactly why exactly barium, right? So here to the right, you are able to see that this will give background free experiment. So the next collaboration is currently exploring the use of custom barium sensitive molecules to fluoresce while chelated, or to be able to grab with barium plus via single molecule fluorescence imaging. So I'll be referring back to this, just an acronym, it will just be SMFI. So let's talk a little bit about the sensitivity of a 1-ton detector. So sensitivities specifically for NEXT, according to how the detector is made, you can see that it's plotted here to the left. We can see how the incorporation of pure materials increase the sensitivities. So the red line is NEXT with barium tagging. So this would provide a substantial increase in sensitivity improvement. So through this combination of signal efficiency increase, we would get an extreme background reductions. So this would mean this would give such an amazing result if we want to incorporate barium tagging. So let's talk a little bit about the ionic charge state in liquid, in both liquid and in gas. So NEXT, as I mentioned before, operates in gas phase. Studies have demonstrated the beta decay recombination rate is suppressed. This leads to a dominance of a plus charge state of barium following double beta decay. This means that barium will only be available, will be the only available atom in the active volume. So this is just an outstanding advantage of barium tagging. And so a talk by Sara Lardini on Wednesday also exhibited the lack of recombination for xenon gas. So just a restatement of how amazing it is to deal with in a gas phase. So coming back to what single molecule fluorescence imaging is, so this is when a non-fluorescent molecule becomes chelated or grabs and becomes chelated upon chelation with an incident ion, becomes fluorescent upon chelation with an incident ion. And so this is a biochemistry technique that can demonstrate a single ion resolution. And so here the image to the left demonstrates the before and after blue light is shined to the molecule with a dye of interest. And so the barium becomes fluoresces. To the right, a demonstration of the single step fluorescence trajectory indicating individual ions. This has been made in our laboratory at UTA. And so how exactly is this? So through this sudden off transition, the fluorophore transitions from an on to off via interaction with any oxygen species in the area. So this helps demonstrate that the single fluor instead of like a white side of multiple fluors. So this gives leeway to understanding where exactly the ion is. And that's exactly what we want for barium tagging. So if now this amazing photograph. So if we were to focus, I always ask this, but if you focus on one of the single bright spots on this image, you see that each dot is a single barium ion that fluorophores. So if you focus on one dot, you're gonna see it light up and then it's gonna light off. So to the right, you see the transition of intensity of this on and off if you were to zoom in. And to the left, you see a schematic of the microscope and laser system that's being developed. Okay, so there are problems that have risen from dry sensing with exactly with the flow group. So the previous molecules would require a deprotonation of carboxylic acid to accept the ion. Therefore, fluorescein does not shine in dry, it will not shine. Currently at UTA, the development of a new molecule that when excited with fluorescence in dry phase is being explored and it's being investigated. An international program of barium tagging R&D has been initiated within NEXT. As shown, the US activities have demonstrated custom turn-on molecules designed for selectivity and sensitivity. This has led to individual barium plus ions being resolved in dry environment. Along with experiments, simulations have also been exhibited ion imaging, along with confirmation with density functional theory. Our Spanish, on the other side, our Spanish collaborators are working towards a color shifting technique rather than an off and on sensing. So this switches from green to blue upon chelation. The addition of filters removes green light background, allowing fluorescence to separate. The remaining ion will contain two negative counter ions as pictured to the lower right. And so here is a picture of the high pressure microscope in situ. So this is at our lab, used to image over a single barium ion over a millimeter squared surface area. And this has been done in 10 bar of xenon gas. Some components of the microscope, as from the image on the left, contain, some components of the microscope are a sapphire window, which is located before the objective. The fluorescence cube holds the slides that contain the custom molecules, along with an adjustable stages for fine tuning. The image to the right demonstrates an exceptional large area that has been achieved to image single ions. And so once again, some of our images that have been produced from our lab. And just to restate, this has been demonstrated at 10 bar of xenon gas. So now let's zoom out and let's look at the larger picture. Another problem to solve and a key solution to the problem is the ion transportation to the single molecule fluorescence imaging sensors in a barium tagging NEXT design. So one possible concept for ion collection is from large cathode, as we have in NEXT, is through the concentration with RF carpets. So the induced RF field will swiftly push forward the ion to be collected in the sensor. Due to the high pressure and voltage requirements needed for NEXT to operate, developing RF carpets is a just challenging task, but it's something that can be achieved. So preliminary simulations have investigated RF carpets transport at 1 and 10 bar, as well as you could see on the image to the colorful images that the required pitch needed for fabrication of RF carpets has been determined to be close to around 15 micrometers for possible long distance transport at 10 bar. So experimental work is underway within NEXT collaboration for RF carpets in neutrinoless double beta decay detectors. So in conclusion, in order to achieve sensitivities at 10 to the 27 years for neutrinoless double beta decay, the background radiation must be suppressed to about less than 1 count per ton per year. One of the most promising techniques is barium tagging. So which is again, the identification of the barium daughter produced during a double beta decay by a single molecule fluorescence imaging. If we were to couple this with energy discrimination techniques, this could reduce our backgrounds to 0. And this is such an unprecedented feat in signal sensitivity. This is part of a rigorous R&D program across the NEXT collaboration to realize a high pressure gas barium tagging TPC. And so just in conclusion, thank you so much. I know my last talk was the last one for lighting. So thank you for everybody for tuning in, and I'll take any questions.
Thank you, Karen. Are there any questions?
Hi. Can you explain a little bit what about the neutrino mass that you expect from the next result?
Yes. So then, are you referring back to, let's say, something about here, about the neutrino mass? Or can you ask your question one more time?
Yeah, I mean, what the neutrino mass that you expect from the next results after the measurements?
We think it would depend on the nuclear matrix element. Yep.
Okay.
Okay, thanks. Karen, I had one. So one thing that's been clear to me with the barium tagging stuff is like, what's the time like between like the energy in the event and actually tagging the barium daughter? Like, what's the time difference in detecting those two signals that you'd expect?
Yep. So let's say it's about 1 second, so it's pretty fast. It won't take minutes or let's say a long process. It's roughly around 1 second.
Okay, so it'd be you see a barium, and then you go look in the last second or so for the decay, the Xenon 136 double beta decay. That's kind of how the analysis would work?
Yes, it would work around yes.
Okay. Cool, thank you.
Thank you.
Okay, and we ended